Cool. So great presentations from our previous speakers. Thank you very much. I'm very excited to be here speaking today. I'm Carson Coursey. As you can tell, I work for the Avengers. No, just kidding. I work for the Aerospace Corporation. It's a federally funded research and development center tasked with supporting the nation's space enterprise. So I'm going to talk to you a little bit about some of the work we've done along those lines. I think the theme of my talk is kind of going to go nicely with Brandy's talk, where she was talking about space sustainability. And I think some of the key takeaways I want you to have sort of relate to that really well. Oop, went forward a little too fast. Yeah, so I'm here to talk about a problem that's really important to me that I've been working on at Aerospace, perhaps part of a solution that we've been researching. I've been working with my colleagues, Dr. Mark Skinner, who's actually right there, so say hi, Mark, and Eric George. So let's begin. So as we all know, we've been hearing for the last couple days, space is crowded. There's lots of stuff up there, debris, imaging satellites, private astronauts, which is fantastic. There's even a Tesla Roadster up there. So there's all kinds of stuff. But no doubt, driving this boom, and what you largely see pictured here, is large LEO constellations that are seeking to provide access to the internet from space. And these are great satellites. They're doing incredible things for the world. I don't want to disparage that at all. They're providing high-speed internet to remote communities that maybe have never had internet before. They've never really had usable internet, so they're getting that. It's enabling crucial communications during disasters. That's no doubt saving lives. And they're even aiding our allies during times of war, as we've seen in Ukraine over the last year. So these satellites are doing incredible, really important things. But as I think we also know, they've come with some ramifications for ground-based optical astronomy. These metallic satellites are reflecting light down right into the observatories, generating images like this one you see here from the National Science Foundation. But I think we all know this so far. If you've been over here over the last day or two, you're familiar that space is getting crowded, and you probably have heard about the effects on astronomy. But let's back up a little bit and talk about why this happens and what we could do about it, right? So the conditions arise for a satellite to be visible. And when I say visible, I mean having a visual magnitude of around 7. That's generally the naked eye limit. Visual magnitude is just a system that scientists and astronomers use to sort of measure how bright something is in the night sky. So for example, the sun is negative 27, the moon is negative 12, and the naked eye limit is around 7. So the smaller the number, the more negative the number, the brighter it is. And so the conditions arise for satellites to be visible when they're over a spot on the Earth that is in nighttime, so it's dark there, but the satellites aren't quite over behind the Earth, so they're still lit. I remember when I was a kid, I had an app on my phone that would tell me when the ISS was passing over my house. Anybody have that? It's super cool to be able to go out in your front yard and see ooh, there are like 5 people going over me right now, right? So that's the same sort of thing happening. The conditions are just right where it's visible. And it's really cool when it's the ISS, because there's only one ISS, but when there are thousands of internet satellites, it starts to have more of a negative impact on astronomy. So that's why this happens, right? And I do want to underscore that satellite owner-operators have done a lot to try to address this. They haven't just put these satellites up and kind of been like, okay, figure it out, astronomers. They have really tried to help out. SpaceX has had VisorSat and DarkSat over the last couple of years that involved design changes on the satellites to try to, specifically to help astronomy. But studies are showing that the mean apparent magnitude, even with these changes, is still below 7, and that's still visible to the naked eye, and certainly still capable of ruining observations. So there's still lots of work to do for the whole community. Okay, so introduce that problem, but let's talk about a really similar problem that the aerospace community has been grappling with for since the dawn of Sputnik and aerospace and everything, right? So you're in mission control, maybe you're with NASA, with Johnson, you want to be able to point a sensor at your spacecraft, right? If you don't know where your spacecraft is, luckily, the United States Department of Defense operates a public catalog that tells you exactly where your spacecraft is. So that's great. And then using applied astrodynamics, you know where to point your spacecraft. But what if you want to characterize your spacecraft based off of visible light? A lot of people want to be able to point a telescope at a satellite in GEO and try to characterize what it's doing, what it's there for, right? That's a problem that's been around for a long time. But we haven't talked at all yet about, is the satellite actually visible or not? But luckily, some really smart people have developed some models that allow us to predict the visual magnitude of satellites as they pass overhead, using just the angle between the Earth, the satellite, and the sun. Okay, so that's another piece of the puzzle. We know where the satellite is. We know roughly how bright it's going to be, right? But let's bring it back to astronomy. Astronomers actually don't want to look at satellites. That's exactly the opposite of what they want to do. They want to avoid satellites at all costs so their observations aren't spoiled. And maybe you're starting to think about how those problems are kind of exactly the inverse of each other, right? So what if we could use the tools that we've been using for decades to solve that initial problem and sort of put them on that second problem of looking where the satellites are not, or knowing where not to look, right? So that's what we've been doing in aerospace, using some tools that we've had, sort of applying them to this problem and seeing how they fare. And so here's just a concept of operations of how this would work, right? So on the top, currently, there's no predictive mitigation. That's what we call these systems, where you're able to predict and mitigate the effects of satellites. On the top, there's none of this, and observations are readily being spoiled because nobody's doing anything to prevent them. But on the bottom, with predictive mitigation, there are a number of ways that we can help the observers. So in D, this is sort of the classic case that I've been mentioning. The observers know when there's going to be a visible satellite overhead, so they kind of just look other places, right? In E, there's another interesting case where what if we tell the operators, hey, you're going to be visible over an observatory. If you could just tweak your attitude just a little bit, of your spacecraft, then maybe you'll reflect a little less light down into the observatory. So that's another case that can sort of mitigate the effects, right? But I do want to point out that these are not perfect, and F sort of captures that. Not all observatories really operate with principles that this is helpful for. Even then, it wouldn't be a perfect system. Nothing's perfect, but it could be a piece of the puzzle. So now I want to jump into our specific model, right? So what you're seeing here are plots of visual magnitude versus time. So each of these dots is an observation, and the y-axis is telling you how bright it is. And because the smaller the number, the brighter, higher up on that y-axis is brighter the object. So on the left, we have a simulation, and then on the right, we have observations. And you can see there's generally good agreement in the timing and the rough values, but you can also see there's a pretty big discontinuity between the plot on the right and the plot on the left. And that's largely the nature of predicting visual magnitude. These simple phase angle models just can't really capture all of the intricacies that are happening at the location of the observer, such as clouds and the lens changes and the state of the atmosphere and just things like that. So you can kind of get a rough approximation, but it's not going to be perfect. OK, so now what if we actually look at a constellation, right? So similar plots on the bottom, visual magnitude versus time. I do want to point out the time scales are wildly different. In the last slide, it's on the order of 15 minutes or so. This is more a week on the left and a day on the right. And the line there at 7 is the visual magnitude limit. So if it's below that, then it's definitely messing with some observations. So those are the plots on the bottom. The plots on the right are showing you, it's an azimuth elevation visual magnitude plot. So it's essentially showing you where in the sky satellites are and how bright they are. And you can really start to see some interesting things take shape. So on the left, we have just one satellite for about a week. You can see the different passes down below. So it seems during the middle of the week, for this particular event, it seems to be OK. Not a whole lot of visibility. But in the beginning and end of this random week, there are some serious issues as you get down below 6, 5, 4 visual magnitude. One really interesting thing you can start to see on the right, for the entire Starlink constellation for one day, you can maybe start to see some windows popping up. You can see the orbits start to take shape. It could be possible for observers to kind of just to know this ahead of time and look through those holes if that's the kind of astronomy they're doing, right? So that's really exciting. I will point out that this simulation was run in December 2021, and a lot's changed since then. Thousands of more satellites have gone up just since then. So it could be a very different situation, but obviously the satellites are not as big as these dots, so there might still be different windows that they can peer through. One interesting thing I also want to point out is how we see something that we would sort of expect, right? In the beginning and end of the night, you're getting a lot of observations. You see that in the bottom right plot. But in the middle of the night, you're not getting as much. And if you think about it, that's because when you're at the beginning and end of night, you're close to the terminator. The satellites right above you are still lit by the sun. And so we would expect that. But you get this brief break in the middle of the night. So that sort of does a little bit to almost corroborate our results and that we're agreeing with the reality of the situation. And I like to call this sort of the saddle shape, or as it's colored here, the blue jean shape. Cool, so one more important piece of information is how much does the input data actually matter, right? So there are a couple different types of information you can feed into this software. You can have TLEs, which you get from the public catalog that I mentioned earlier. And these are OK, but there's some inaccuracy inherent to their data type, right? So they're not great. But there's also vector covariance messages, which is just a higher fidelity type of data. But because they're much more accurate, they're a lot harder to get. You have to work with the Department of Defense much more closely. You have to partner with them. That can be kind of a challenge. So if TLEs work about as well as VCMs, that's a really good thing, because then astronomers, whoever's using this, can just kind of scrape the public catalog, run the software really quick, and then they'll know, where they can and can't look. And as this plot here is showing the time difference and the maximum elevation of satellites passing overhead using TLEs versus VCMs as the input data. And you can see the time difference is largely clumping to 0 here. So there's a very negligible difference, if there's a difference at all, in the sort of basic astrodynamics when used for this purpose. So that is really encouraging. I want to point out, as I wrap up here, that we're absolutely not the first people to talk about this. We're not the first people to come up with this idea of predictive mitigation inside of the Aerospace Corporation or outside of the Aerospace Corporation. The astronomy community has a really robust and collaborative response to the challenges posed by large LEO constellations. And processes like the one I've discussed are all over their reports. We're just one implementation of this that we can hopefully compare with along the way, and hopefully sort of validate anything that the astronomy community is able to put together. And so I come to the end here. I want to talk about some broad takeaways. So the specific takeaways, large LEO constellations are great. They're doing a lot for the world, but as we all know, there's some ramifications for ground-based optical astronomy, and we're working to try to address that at the Aerospace Corporation. But some even broader takeaways here that I think are really important, especially in this audience, right, is kind of just the role of engineering in society. We are all engineers to use technology to benefit society, and sometimes that means limiting the negative impacts of your technology on society, right? And so this is one tool that can hopefully help do that for large LEO constellations. And as these constellations are definitely here to stay, we're only seeing the beginning. We have a little over 5,000 satellites now, but as we've all been hearing, it could be up at 100,000 by the end of the decade. So this is going to be growing in importance more and more, probably every year. And we need super smart engineers and scientists and space people like in this audience. So it's a really tough problem, and you guys should all help solve it. Cool. And these are my references, and that's all I've got. I'll be around for questions afterwards. Thank you very much.